Hi, this is Luke from Jimmo Heights Bale Wagons. Here today in my coveralls. I'm actually working for once instead of on the phone. But anyway, we're doing some hydraulic troubleshooting. This is a 1095 that a local customer brought into the shop here, so that makes it handy for him and for us. Thought I'd give you guys a little instruction on what to look for, and it's a fairly common problem on these. The 1089 and the 1095 system are pretty much the same, and they're real similar to the later BW and H series machines, so hopefully this will help you guys out. So I'm gonna go ahead and start this machine up and kind of show you guys what it's doing. It's basically got real low hydraulic pressure to the first table, second table, etc. Cross conveyor chain's running normally, but when I go to trip the first table or the second table manually, that's what we have issues. Okay, as you could tell in the previous video, when we ran the engine, had the hydraulics engaged, put the computer in the manual mode, you could see the cross conveyor chain would run, and if I would have raised or lowered the bale loader cylinder would have raised the bale loader chain would have run. We were only getting slight movement out of these first tables and none at all out of the second. Actually, you'll notice that the auxiliary table come up a couple inches. When I triggered the main table, it wouldn't raise at all. So the reason we're getting some hydraulic action and not others on the 1095 and 1089, Holland put in a split system. So we have a gear pump. It's mounted right on the timing case of the engine. That runs the steering gear, runs the power brake booster. It also runs the bale loader cylinder, bale loader motor, and then the cross conveyor chain. For the closed center system, they use a piston pump that's mounted right on the front of the engine. On the earlier ones like this, they are basically mounted right onto the harmonic balancer. Some of the later ones, they had a remote drive shaft. They also had a kit you could remote the pump, which is a lot better system. You'll see a lot of these, they vibrate a lot. They can break the shaft pretty easy doing that. Anyway, all that oil flow from both pumps gets put into this aluminum manifold. So it's kind of a combined system. It's a lot more centralized. It's better than the old systems where you had valves here and there and hydraulic lines running everywhere. So both oil flows come in here. The gear pump side is a separate from the piston pump. That way you can run them both simultaneously. So with this combined system, it's a lot better setup than the old machines. The old machines only had a gear-driven pump, so as the gears rotate in the pump, obviously the faster the engine rotates the pump, the more oil flow you're going to have through the system. When they went to the automatic transmissions, they went and split the system. So the stuff that's kind of important, you need oil for all the time, like the brakes or the motors, that's run off the gear pump. Stuff that's on demand, like the tables, load rack, second table, first table, spikes, that stuff's just run when it needs. They do that through this piston pump. It's a variable displacement pump, which is kind of cool because if you're idling through the field and heavy bales, bales are pretty close together. Without automatic, you can't be revving the engine up all the time. It's just kind of idling basically. So with this pump, it has a cam plate inside it that basically will stroke and de-stroke depending on the conditions that the hydraulic system is seeing. That allows it to basically have almost the same flow at idle as it does at full RPM. So to get the piston pump to basically see what the hydraulic system needs, they have a thing called a load sense. There's a section on the pump that I'll show you later that's looking for pressure. So when there's a lower pressure, it'll stroke the pump up. When it's a higher pressure, say you got the second table all the way up and it's pinned, it'll maintain that 2000 or so psi and stop flowing. It'll de-stroke the pump. And that's done through a circuit. It's a feedback loop basically from this. It's basically from the output side of the pump. And it comes through the manifold and then back to the compensator on the pump. Now this combined system is a good system. I like it. It's a huge improvement over the old wagons. But there's a few things about it, particularly on these 1089 and 1095s, kind of the first series, that have some issues. One of the problems is this gear pump being driven off of the timing cover. If that pump gets worn, which is common on a gear pump, sometimes the teeth can get basically jammed, and when that happens, it'll shear the shaft, is what it's supposed to do. But a lot of times, if that shaft is sheared, that gear is just floating around there, and it can blow up your entire timing set, which means your engine needs basically an overhaul. That's one problem. The second problem is on these manifolds. They were built back in the late 80s, early 90s by the Vickers company, and they did a good job, but back then they don't have the manufacturing setup that we have these days. So a lot of these manifolds you'll find have cracks in them. Sometimes they have a fitting blowout. These were available for a long time from New Holland, and then they decided to quit building them. So we actually re-engineered them, had a company that knows what the hell they're doing. They put it in their computer system. They found some of these passages are too close in a tolerance, so that's what causes the cracking internally. So about the only thing you can do is replace it, but we have these usually on the shelf now. Most of the valves are available. Sometimes they're a special order, so they got a big lead time, but we tend to stock a lot of the more common ones that can give you trouble. So if you find you got any issues, give us a call. We can usually help you out over the phone. Okay, getting back to troubleshooting. There's about 3 things you need on these wagons to really do a good job, and I use them all the time myself. First thing, you better have a manual. The 1089, 1095 manual, like you see here, it's about 3-4 inches thick, and it's probably the best manual New Holland ever did on these wagons. The second thing, if you're doing hydraulic troubleshooting, you better have a flow meter. You want one at least 30 gallons a minute, maybe even more. 35, 40 should be fine. You want yourself a nice set of pressure test gauges, and then you're going to need all the hoses and fittings to adapt it into the system. Third thing you need a digital voltage meter. Don't use a test light. It may work, but a lot of times test lights don't show you the actual voltage going to the coil, and that's very important on these machines. Obviously they're electrically controlled computer system. It's driving these individual coils. These are all 12-volt coils on this machine, so at least have a decent meter. There's really no excuse to have this kind of equipment and not have one anymore. I've got some custom stuff I set up over the years, some breakout boxes, make troubleshooting a little easier, but it's not necessary. I'm going to go off on a bit of a tangent. If you're using local techs, make sure you got somebody that knows bale wagons. If they've been working on rotary mowers for some lawn service outfit, dealer sends some kid out, third day on the job, you're going to have issues, because if the tech doesn't know the bale wagon and how it's supposed to operate correctly to begin with, you're going to have a lot of trouble and a lot of expense and time teaching them what's wrong. And more than likely they'll just start shotgunning parts, and your bill's going to get pretty expensive. If you got any problems, give us a call. A lot of time we can talk you through in a few minutes on the phone. Do a diagnostic service call over the phone. If I have to, I can fly out to you. Make sure you got somebody who knows what they're doing. It'll save you a lot of hassle and headache. So let's get started troubleshooting this particular wagon. So anyway, we talked about the pump. There's a pretty good sized hose that runs. It's the main pressure hose from the pump. It goes right into the big aluminum block. It feeds a big oil galley. That galley feeds basically all of the hydraulic functions like the load rack, second table cylinder, first table cylinders, tie spikes up and down. Each one of those functions has an electric valve. It also has a load sense valve that basically loops around back to the pump, to that compensator. There's 2 orifices in that system as well. There's a 73 thousandths orifice. And once this valve opens, it pours oil through that orifice, back through a hydraulic line to the compensator. And that basically allows the pump to read what's on the system pressure. And if it needs to increase the flow, it will, and eventually the pressure. And there's a 26 thousandths orifice that runs back to the tank return. This orifice, the 73 thousandths, basically keeps the pump from being shocked every time, you know, this valve opens and closes. The 26 thousandths orifice, that basically, if there's any oil trapped in here when this valve closes, it can drain out and basically allow the pump to be de-stroked if it's back in idle. These 2 are pretty important, and we're going to show you here in a minute what happens if something goes wrong. So let's get on the machine. Okay, so I've already got our 0 to 3000 psi pressure gauge hooked into the gauge port for the piston side of the manifold. Got a breakout box here, and I've got a digital multimeter so we can tell basically with the load sense valve coil is getting voltage to it or not when we actuate one of the functions. So I'm going to start the machine. You're going to see the standby pressure is about 200 psi off the pump. We'll maintain that, and then even when I try to trigger some of the functions, it may jump around a little bit, but it's not going to get much above that. Anytime you cycle one of the, say the first table cylinder and it comes all the way up in deadheads, or the second table cylinder, you should see it go from about a 200 psi standby all the way up to about 2050 psi and maintain that. As long as you're holding the key down manually, or the computer is tripped. But usually the computer will just trip it up and down and release it. So I'm going to start the machine. You're going to see that 200 psi no matter what I do. Okay, as you saw, we just have standby pressure no matter what we're trying to make the machine do. That tells us something in that load sense circuit is probably not working properly. Being we have second table, first table, load rack, push-off feet, tie spikes. None of them seem to be working right, or if they do, they're moving slowly or not at all. So on this manifold, the load sense valve is this valve here. It's got a 12-volt coil around it. I've tied into that harness. I've got our digital multimeter here. I've got the computer in test mode, so we can trigger this on. We should see about, you know, somewhere around 12 volts on the meter. And if you can listen to it while you're standing here or have somebody trigger it in the cab, you can usually hear it click. It's moving the solenoid valve. So let's see what it does. There we're showing about 10.5 volts. A lot of times you can take something ferrous and stick it on the end. It should stick when the coil is activated, and it is here. So we know our coil's working. We're pretty sure our valve is working, so let's check that next. Okay, so we've pulled the load sense valve out. We're going to look at it. This is a poppet valve. It's basically an on-off valve. There's several types of these, and they're all in the same package, so make sure you got the right one. This one's what they call a normally closed valve. That means it's closed all the time, except for when the coil energizes the actual poppet valve itself. There's a little piece in here on the inside that you can take a pick and you can move it back and forth. Check that to make sure it's moving and not stuck. And then when you have the coil on there, you can activate or energize the coil, and you should hear this click. You may not see this actual spool move against the spring, but what that does is there's a pin on the very inside of that assembly, and that's what the coil moves. It unseats the pin, which allows the oil to unseat the actual poppet itself. The rest of the time, oil reverse goes through a set of orifices and keeps that closed. So it looks like this one's free, it's moving, doesn't appear to be stuck. So I think we're good. Okay, so this is the actual hole for the load sense valve cartridge. You see here it's marked LS, it's stamped on the block. All these positions that have any kind of valve or relief cartridge or flow cartridge or anything are marked that way, even if it just has a fitting for a hose. This orifice is what they call a disc type, and this sits underneath the cartridge when it's inserted into the cavity. You can pull it out sometimes with a pick, or they're steel, so you can use a magnet on them. Thing you want to check on these, make sure it's not plugged. Look at the hole, blow it out. This one's clear, obviously. If this gets plugged, that won't allow any oil to go back to the compensator, so that's one of the things we want to check. You'll also notice that it has kind of a spherical or a tapered fit on one end. On all these discs like this, the taper always goes towards the block, because what it does is the valve face will come up against the flat, and that's how it sits in there. And if you get it in backwards, it can screw things up, won't seat the valve properly, etc. So always make sure you get that back in properly. And then we're just going to put the valve back in. Okay, so we've checked our valve, checked our coil, we've heard it click, we checked, looked inside it, noticed it was moving properly. We looked at our orifice disc, it was clear, didn't have anything wedged in it, blocking the flow to the load sense port back to the pump. So we're pretty confident that that circuit's good. So what else do we look at? Well, I already went in my DeLorean, I've been to the future and back, so I know, but we need to look at this 26 thousandths orifice. This is a pretty big problem on these older machines, all the way up through the, in fact the new ones pretty much use the same setup. This drain orifice is a plug, so it's basically an ORB plug that they've drilled an extremely tiny hole in. If that gets plugged, the pump will remain basically stroked all the time. So instead of seeing that 200 psi at our gauge like we did, you're going to see like 2000 psi all the time. That's hard on the pump, it overheats the oil, there's a lot of reasons that's bad. So they put this little orifice in here. It's big enough it can drain back to the tank, but it's small enough that it restricts the oil, so the oil basically just flows back to the load sense port on the pump. What can happen is, since that plug is about the size of my pinky, if it unscrews itself into the cavity, that goes from a 26 thousandths opening to like a 5/8 of an inch opening. So the oil can just dump straight back to the tank. So the next thing we're going to do is open the external cavity plug and look in and see what we got. Okay, here we are back to the manifold. We got in the book, we know which port plug to pull out. That's our external port. Underneath it, if you look down inside there, you'll see the plug with the tiny hole in it. Look at this, it's loose. That's not good. That means it's getting almost unrestricted oil flow through that load sense circuit and dumping it back to the tank. So I'm going to take, these are magnetizable as well, they're steel, so you can use a magnet. Okay, see, here's our plug. The hole is open. See how tiny that is? What usually happens is the O-ring deteriorates and vibration and just hydraulic cycling for 20 some years allows this to get loose. In fact, the O-ring fell off of this one, so probably the O-ring just went bad over the years. and eventually it just unscrews itself right out of the threaded portion. So we check that, make sure it's open. We're going to screw it back in with a new O-ring and see what happens. Okay, so we got everything reassembled like it should be. So I'll put it back together, coils on, snap down. We're going to fire the machine up. I'm going to activate the first table. We'll see the standby pressure is our low pressure setting. And as soon as the table comes up to the limit of its travel in manual mode, it should show about 2050 psi is where we have our high pressure cutoff settings. Let's see what happens. Well, as you can see, our table's magically moving again. If I were to run the rest of the function, they'd function just fine as well. As you notice, standby pressure again is 200 psi. As soon as you command a table or a function to move, you'll see that pressure increase as the system sees demand for flow. Pressure usually follows flow. And then once the table comes to the stops, the cylinder was traveled out and can't go any farther, so the pressure goes up to about 2000 psi. That's what we want to see. That's a normal system. So hopefully this helps. If you need parts or service advice or want to talk about buying a different machine, just give us a call. That's what we're here for. Have a good day.